In Part 3, System Sizing and Specification, we'll outline how to select the appropriate heat pump for an installation. The learning outcomes for Part 3 are understanding the primary goals of an air source heat pump installation, learning how proper sizing supports design goals, and understanding key design considerations for mini-split and multi-zone air source heat pump systems.
Welcome to Part 3. This presentation outlines how to select the appropriate heat pump that would be installed. The learning outcomes for this part are that the end goal of the heat pump installation project should be kept in mind throughout the sizing and selection process, not only in terms of what's commercially available, but also in terms of the homeowner's needs and expectations. Providing enough heat where it's needed is essential in any heating spec, but having too much heat can also lead to comfort, cost, and durability problems as the heat pump short cycles. The use of multiple heads with one outside unit has a tendency to lead towards overheating in some zones. We'll talk about possible alternative ways of handling an imbalance in heat load. The basics are, though, that installers should only be installing heat pumps that are recognized by the Air Conditioning, Heating, and Refrigeration Institute, the AHRI. All split units should be AHRI matched. In other words, the outdoor unit must be the same make and model as the indoor model. Extended performance data that gives output levels of the heat pump at different outside air temperatures must be used as a key element in the selection process. And in that selection process and looking at the extended data, that should come from either the NEAP database or the manufacturer's database that outlines performance and capacity, or the efficiency and capacity of the selected heat pump. Heat pumps should also be sized for the heating load first, and then the cooling load. And you'll probably see the reason for that a little later. Sizing the heat pump forces you to consider many, sometimes competing goals for comfort and cost. These are three of the most relevant energy comfort related considerations. Obviously, the heat load of the home needs to be met on the coldest day. What may not be so obvious is that the load should be met rather than exceeded. The second most important factor when it comes to sizing is turndown ratio. How low can this unit go in terms of its performance and still meet a design capacity and an efficiency level? Not providing too much heat on mild days means closely following load profiles while maintaining system efficiency. The overall effectiveness of the heat pump installation project also depends heavily on the quality of the delivery system and its match to the home's thermal and comfort requirements. This slide summarizes the reasons for right-sizing the heat pump. The advantages to right-sizing are greater occupant comfort, higher energy efficiency, longer equipment life, and increased reliability. If a system is sized too small, then it will not keep the house warm on the coldest days. Additionally, a unit that is sized too small may be slow to catch up after the overnight setback. A system that is too big will inevitably cause short cycling, resulting in poor energy efficiency, shorter equipment life, less reliability, and poor occupant comfort in terms of temperature, draftiness, and noise. Oversizing will also increase the equipment cost. This slide shows a visual of an oversized heat pump on the left and a right-sized heat pump on the right. Along the horizontal axis are time periods in 3-hour increments. Along the vertical axis are units of kilowatts of electrical power in increments of 1 kilowatt apiece. The oversized unit turns on and off, as you can see from the graph, about 5 times in 3 hours, whereas the right-sized unit only turns on about twice in a 3-hour period. So why is short cycling in the selection of a heat pump so important? It's important for a couple of reasons, but the main one, it focuses on efficiency of the unit. When a unit is oversized, it can short cycle and cause a reduction in the coefficient of performance somewhere between 15 and 40%. And then if you take a middle number, say 20%, that would mean that the COP, instead of being 5, it would really operate as more of a 4. There's also an impact on the equipment life and the comfort of the occupants. By reducing the overall energy performance during low load periods, that also contributes to lesser efficiency. And by this, we mean when the outside air temperatures are warmer and the load is lower, under those conditions, with a right-sized unit, particularly one that's capable of adjusting to lower loads and lower levels of operation, it can recover these parasitic losses from running in a piece of equipment that's much larger than what's needed to meet the load. Short cycling isn't as critical as failing to meet the design load, but the impact is important and it shouldn't be neglected. For partial load displacement, that is where you're using a heat pump with some sort of other either backup or supplemental system, it is a more critical factor in sizing the unit. This chart compares the range of variable capacities of models with a nominal capacity of 1 ton for ductless air source heat pumps, various manufacturers. Each of the blue lines, these vertical blue lines, represent the range of capacity for a different heat pump model. So we have a total of several here, of about a dozen, but they all have a nominal capacity of 1 ton. In other words, we're looking at installations that are very close to a nominal 1 ton worth of capacity. Note that the maximum and rated capacity of the first 3, now this is the maximum rated capacity, these are all about 12,000 BTUs. The model on the far right, this one here, has a wide range of capacities. It can go as high as 24,000 BTUs an hour and all the way down here to 3,000 BTUs per hour. Note that the rated capacity on some of these models to the right are generally a bit higher than their nominal capacity, actually quite a bit higher, because these have a nominal capacity of exactly 1 ton, whereas these are actually models that are slightly larger. And their rated capacities are going to be as high as 16,000 BTUs an hour. This bottom line is important down here, though, the ones that can come down as low as 3,000, because this is where the low load conditions will be met. Now, you may be wondering why some of these models actually have a higher rated capacity than their nominal capacity and how they can actually operate at actual capacities above their rated capacity. And the reason for that is these are generally larger, more robust units, more expensive in most cases, and they also have a more granular means of being operated. They can operate over this wider range by having a design that allows the refrigeration cycle to slow up to the point where it can still be energy efficient at low loads as well as very high loads. So the one to the right would be the one, if you wanted, it can certainly operate efficiently as the others within its mid-range, but they're more capable of being able to perform efficiently over this wider range because of increased surface area, the ability to vary the flow of the refrigerant, as well as speed down the electric motors for the compressor and the fans. This is similar to the previous one, except it shows heat pumps with a nominal capacity of 2 tons. But note that the second and third models from the right have an actual capacity of 36,000 BTUs or 3 tons and have a turn down ratio of 9:1. So these are very versatile units. They can operate over a wider range efficiently and operate over a wider range in general. The ones on the right can go, in this case, down as low as 4,000 BTUs an hour and as high as 36,000. So again, that's a turn down ratio even higher than the last slide of 9:1. This slide is included in part 3, selection and sizing, rather than part 2, load calculation, because it underscores the importance of turn down ratio. Climate zone 4 here on the East Coast is represented by this gold colored vertical line in the graph. On the right-hand side, you have hours of the year, the number of hours that it operates at a certain load level. And then underneath, it's correlated to, on the horizontal axis here, to outside air temperature. So looking at the gold bars to the far left, you can see that the number of operating hours per year at -3 degrees are very, very few. Same at 2 degrees. 7 degrees. And as you go up in temperature, the vast majority of the operating hours are between 22 degrees Fahrenheit and 52 degrees Fahrenheit. So in this outside air temperature range, almost all of the operation of the heat pump will take place in that temperature range. And why is that important? Well, it's important because in order to cover this range efficiently with the heat pump should be able to modulate its capacity. And the most important part of that range where you are modulating the capacity is between 22 degrees outside air temperature and 52 for the climate zone 4. The other hours that fall outside are very few and far between. You can see the number of hours at 17 degrees is probably only around 60 hours a year. So that's, really taking cumulatively, it would be 2.5 days. But in reality, that temperature level is generally not even for an entire day. So by comparison, if you look at the light blue bars, those represent temperature hours in climate zone 5, which is a little colder. And as you can see, the number of operating hours at the lower temperatures are higher than they are in climate zone 4. For example, here at 7 degrees, you have about 75 hours a year. So that the range that you would want to have your heat pump cover would be a broader range than you might have in, say, climate zone 4. In climate zone 5, you might want to include it down to, say, 7 degrees, as opposed to the range between 22 and 52. So let's look at a variable capacity heat pump and how it modulates to meet load. And in this particular case, we're looking at a nominal 4-ton capacity unit at 47 degrees. So that's indicated by this red circle. The upper line here in blue represents the upper limit, or the maximum or actual capacity of the heat pump that it can produce at a given outdoor air temperature on the bottom. So this, at design temperature, which is indicated in green, and it's at 7 degrees Fahrenheit, is shown with this vertical line here. The performance of this unit, therefore, then, at 7 degrees, it can still make as much as 40,000 BTUs. As the temperature goes up, its ability to produce more heat goes up, and it can make as many as, say, 55,000 BTUs an hour, up in the low to mid 50 degree range. The lower bar, represented with this red colored line, represents the modulating turn down rate. In other words, how low a capacity this heat pump can operate and still be efficient. And then the modulating range would be everything in between its maximum capacity and its minimum capacity. If we're operating above the maximum capacity of the heat pump, it'll have insufficient capacity to meet the load of the home, and it'll require some sort of backup or supplemental heat. If it's operated below its minimum capacity, it'll short cycle and it will be inefficient, and it can result then in shorter equipment life and occupant discomfort, as well as increased cost to operate the unit. This slide shows various different makes and models of heat pumps and how some modulate differently from others. On the left-hand scale is capacity in BTUs, and on the bottom scale is outside air temperature. So looking up at the top row in the middle, that's an example of a heat pump that has a fairly low turndown ratio. In other words, it can't modulate lower temperatures. The capacity drops off fairly dramatically compared to some others. And that is an example of one. And this one is an example of the same thing. And then some products, when the outside air temperature goes lower, they tend to decline in their capacity as well. And you can see here on this, in the second row, the first box rather in the second row, where see how the capacity is quite a bit lower as the outside air temperature declines compared to others, where the capacity is still somewhat high at the lower temperatures. And these would be other examples of that. And then some products actually maintain near nominal capacity, even at low ambient temperatures. This would be an example of that here. The bottom far left-hand graph is, you can see where even though it's at low temperature here at about 5 degrees Fahrenheit, it still maintains the capacity of almost 30,000 BTUs. So as a contractor looking at various makes and models, you want to be able to meet the heat load at low temperature, but depending on what the load is at low temperature can depend on what heat pump you select. If you're in a warmer climate, as an example, a heat pump like this one on the top row in the middle, it doesn't have much low-end capacity, but you may not need it. Ideally, though, if you're in a colder climate, you probably are looking for increased capacity at lower temperatures. And examples of that would be the second one at the very bottom, as well as this middle graph here. This represents heat pumps that have high capacity at the higher temperatures, but also maintain a relatively high capacity on the lower end here at 5 degrees. This slide basically shows the same as the one previously shown for a 4-ton heat pump, but it shows the design condition here. And looking at the design temperature in this case, it's 7 degrees Fahrenheit. And that calculates out to a 48,000 BTU load. And the load design, as the temperature rises, you can see that the load goes down linearly here. However, this design point of 48,000 BTUs is not going to be met by this heat pump without some form of supplemental heat. And that's represented by this triangle here, pinkish color. This point is called the balance point. That's the point at which the design load and the design capacity of the unit are coincident. So in this case, the design load is up here, but this represents the load that the heat pump can actually achieve at this temperature. And so it'll meet the load here, but it doesn't really meet it at the design point of 7 degrees. Also, you'll see that there's still a fair degree of short cycling here above 32 degrees. And this range in here is the range that you want your heat pump to operate in as long as it can meet the load and avoid short cycling, which this one in this particular case does not do. However, this heat pump might work if the house were located in a different climate zone. So if we looked at a design temperature of, say, 15 degrees Fahrenheit, you could meet the load of the home at that higher temperature. However, you still are left with a problem with short cycling on the upper ranges of temperature. Now, what does this represent? Well, here's the original load line. And if you calculated your load incorrectly and you had this higher load, the requirement here of about 60,000 BTUs, this pump would not meet that condition, but you might want to do some improvements to the home to try to lower the load at low temperatures, which is represented by this lower line. This works as far as meeting the design load at the coldest day of the year. However, when you get up to the warmer temperatures, say above here, 28, 26 degrees, now your short cycling problem has even increased because you have the same heat pump with a lower load, and it shifts the whole load line to the left. And now you're going to short cycle at a lower temperature. Now, this is a different heat pump, but much better at meeting both the high loads and the low load condition. And you can see we have this 7-degree design temperature, and the load is actually somewhat exceeded by the capacity of the pump at 7 degrees. We said it had a 48,000 BTU load, and this pump is actually capable of producing at that temperature about 50,000 or a little bit more BTUs. And you can see there is still some short cycling, however, far less, and a certain amount of this at these higher temperatures may be inevitable, but it's a short cycling period. So this pump is a much better selection for the design load, and you can see it'll meet the temperature at 7 degrees Fahrenheit, and in the upper ranges of temperature up close to 50 degrees, it will still modulate down to a point where you have very little short cycling. So to further give an example here, the goal, number one, is to meet the home heating load on the coldest day. And in this particular case, the coldest day is defined as the design load at 7 degrees Fahrenheit, which calculates out to a load of 28,450 BTUs. So looking at the market offerings, what's out there in the marketplace from various manufacturers and their different models that might meet this load? Well, if we looked at the NEEP and the manufacturer's data for a heat pump that is rated at 21,400 at 7 degrees Fahrenheit, it's just too small to meet the peak load. And if we look at another one that has a larger capacity of 40,850 BTUs at 7 degrees, it's just probably way too big for the load. So this leaves us with a choice of a heat pump, a specific one that's available at 31,743 BTUs at 7 degrees. So at goal number 2, then, besides meeting the load, is not providing too much heat on mild days. So we've already looked at the 31,743 BTU unit at 7 degrees, but there's 2 other offerings that are close to that. One at 28,600, but its output on warm days can only go down to 16,600. So that's not even a 2-to-1 turn down ratio. So we can eliminate that one as a choice. The second one that we looked at previously is a little bit better in that regard. It has a slightly higher rated capacity, but its turn down ratio is still only about 2.5 to 1, not the best. It's going to be a lot of short cycling on warm days. But there is a heat pump available with a capacity of 32,900 that can go down as low as 7,460 BTUs on a 47-degree day. So that would be the best choice in this particular case. So now goal number 3 is to select the right product for your need. And the 3 basic considerations here are efficiency, the features and functions available, and the price. As far as efficiency is concerned, we want to look at units that have a heating seasonal performance factor of greater than 10 and a SEER, or seasonal energy efficiency rating, during the cooling mode greater than 15. Again, you want to consult the manufacturer's extended performance data, and that may have even a greater degree of granularity as far as efficiency ratings, and that can help make your decision a little more precise in terms of optimizing a particular unit for the house in question. As far as efficiency is concerned, today we don't really look at the EER per se, the energy efficiency ratio. It's more of a case of what is the efficiency of a particular unit over the course of a heating season for a particular climate zone. And what this does is it takes into consideration the bin weather data. So the overall efficiency for heating is rated on a seasonal basis. And when we distinguish heating from cooling, in that the heating is rated in its heating seasonal performance factor. So what we want to do is concentrate on those units that have an HSPF greater than 10. When it comes to cooling, again, there's a seasonal factor that's a result of bin data for a particular climate zone. And the preference here is to exceed 15 whenever possible for the SEER rating. As far as other features are concerned, there are a host of other types of controls that are available. There's some that can be controlled remotely with your cell phone. There's others that will integrate well with backup heat. There's some that have actually incorporated some AI features where the unit will learn, based on prior operating situations, the correct level to be applied to the heat pump. And then noise rating, something that you don't hear a lot about, but it's actually an extremely important feature, because some people, it's like temperature. Some people, they don't even hear it. It doesn't bother them. Other people, it drives them nuts when they hear too much noise. So again, this is something that you may want to discuss with the customer, and you may even want to have them listen to a particular unit that's installed somewhere else for them to decide whether it's going to meet their expectations in terms of noise. Price is always a factor, and as a general rule, the more efficient a unit is, more expensive it usually is. When we look at the multi-zone or multi-split design, we want to consider a couple of things. How often is the room actually used? You can see here in zone 2, it's kind of an isolated wing of a building. Not sure exactly what kind of room, but it might be, a bonus room or something like that doesn't get used very often. And then zone 3 is made up of the bedrooms. And in this case, there's probably multiple bedrooms, generally around 3 bedrooms in the home. And there you may have 3 separate heads, 1 for each bedroom. And then the general living area downstairs is another zone, one of the larger zones in the house. And there may be certain sections, though, of the downstairs that don't get used very often. In this case, they're talking about a mud room, but it could be another room, a powder room, or a bathroom on the first floor that's small, but doesn't really have a high heat load compared to the other areas. And so in that case, a supplemental heat in the form of electric resistance heating, either through the floor or a direct heater in the wall, may be appropriate. Now, in this case, we're talking about avoiding oversizing and particularly overheating in a particular zone. And what happens when one zone is calling for heat and another isn't? Well, in these cases, first of all, you want to, again, we mentioned the fact that you shouldn't really have more than 3 heads for one outdoor unit. That makes it much more difficult for the unit to match the load in any particular zone. It can impact humidity if it short cycles, and that can cause a problem. And also, you want to confirm what the turn down rate is going to be in a particular zone.
Now in part 3, we learned that we need to meet the home's heating load on the coldest day and have a turn down ratio that allows for not providing too much heat on a mild day and still operate at high efficiency. The installation's effectiveness is also dependent on the quality of the delivery system and its match to the home's thermal requirements. We heard that systems that are too small won't meet the loads. Systems that are too large won't operate efficiently or provide comfort, and they'll cost more than they need to. Right-sized equipment will provide comfort, higher efficiency, longer equipment life, and increased durability. And we saw that there are key design considerations for using mini splits or multi-zone systems based on a home's configuration and how often spaces are used, and whether breaking it into zones or serving individual spaces with mini splits will more effectively serve the thermal loads.